Good day, viewers. Welcome to Cayman Physics tutorial. Today, I'm going to be teaching you something very short and very simple. What we are going to be looking at today is easiest way to derive the kinetic energy formula using algebra and calculus. Today, I'm going to be using these two methods to teach you how to easily derive the kinetic energy using algebra method, or you can also use calculus if you are very good with math. I'm using these two methods because it can be more simplified. You can choose the one that is better for you and the one you can easily understand. And there is a need to prove or to know the formula for kinetic energy. Kinetic energy is simply the energy that is possessed by a body, possessed by a body due to its motion. Right. So when a body is in motion, it is expected to possess a particular energy while it is in motion. It can be a body, a mass, or an object. So while it is in motion, you expect it to have a particular energy. That energy is called kinetic, means like a moving motion or a moving energy, right? Like kinetic can also be referred to as dynamic energy, or like the kinetic can be called dynamic or like moving energy, right? So instead of saying kinetic, you can call it dynamic energy, or you can also call it moving energy. So when a body is in motion, you expect it to have kinetic energy. Now, kinetic energy depends on two major things, which is the mass of that body and the velocity of the body at which the body is traveling, right? So I'm going to be starting with algebra first. I'm going to be starting with algebra, and I'm going to show you how to prove kinetic energy very short using the algebra method. Yeah, we are going to be starting from here, and this is the first one we are going to be looking at. Now, if you want to solve using you want to do the derivation of kinetic energy using algebra, right? The first thing you are going to do here is to introduce the work energy theorem. There's something we call the work energy theorem. It's a basic principle in physics. So you introduce the work energy. It's a theorem in physics, the work energy theorem, which says that typically it says that the change in kinetic energy will give us the work done. So what it says is very simple. What it's just saying is this: is what it says is that the change in Ke is actually equals to work. That is the work energy theorem, right? That's if you the W there is the work done, then the Ke is the kinetic energy, the change in kinetic energy, right? So that is typically what it says, right? So and then from work you can assume that you also know what work is. That is the first times displacement. But now we are trying to move this from a point of rest to because we're talking about motion now. So a body that is in motion will have actually started from rest. So when you want to break down the W, you can actually break down that W here. You can break down the W by bringing in its formula. Also, we know that the work, right, is force times displacement, or you can say force multiplied by its change in displacement, right? So you can put that back there. So you can also say that the change in Ke is equals to work, and that work is force multiplied by the change in displacement, because the body now has to start from rest, right? So that is the reason why you see me bringing that in. The body has to start from rest. So after you must have done this, right, so you can't stop here. This is the introduction. What I've just done here is to show you that the change in kinetic energy will be equals to the work using the work energy theorem, and I introduce the formula for the work, right? So the next thing we are going to now is I'm going to show you. Next thing to bring in is to introduce the second law. Second law of motion. Second equation, I mean. It's the second equation of motion. There's a difference between the laws and the equation. The laws are what we state. The equations are the formulas we write down, right? So what we are introducing here is the equation, right? So you know the equation, one of the equations that says introducing kinematics. We call that kinematics equation. Right? So we will bring in the third equation. Let's use the third one. Very simple. Let's use, which says that high A, it just says that V squared is equals to U squared plus 2A. Now we are going to be using change in X. It's supposed to be 2AX, but now we are using change. Don't forget, we have been talking about change in displacement, so we have to use that as well. So that's what we are going to bring in. And then don't forget that we already have S here. So you just make here, you just try to make your S the subject of the formula. So if you make that the subject of the formula, you are going to have, you can move this out first. You are going to have V squared minus U squared is equals to 2A change in X, right? So from there, you can make the change in X the subject of the formula, right? So the change in X there can be V squared minus U squared all over 2A. So you are going to have this. Right. So this is what you are going to have. I've made this change in X now, which we are seeing here. The change in X we are seeing here has been replaced as this. Right. So as this now, right? So that is the change in S, which I have just derived an expression for. So the next thing you are going to be doing now, very simple, is to now introduce what you have just gotten now, right? You introduce this into that change in K, right? You introduce this change in X that you have gotten here, you put inside the change in K. And don't forget what we wrote as a change in K the other time. We said that that change in KE, we said it will be equals to work, and it will be equals to F change in X, right? So from here we can say change in KE will now be equals to, let's consider the F of X, F change in X, right? Let's consider the F change in X directly. So that F change in X directly, we are just going to be putting the change in X and put it into this place, right? So if you put it there, you can also break the F further by having F. The change in X now, what are you going to have there is going to be, this is the multiplication. You are going to replace all of these things, which is going to give us V squared minus U squared over 2A, right? So from there, you can also recall what your F is. You call that F is equals to MA, right? So if you substitute that one into this itself, if you substitute that into this, right, you are going to have change in KE, which will now give us MA, which is for the F, which you are now going to multiply by V squared minus U squared all over 2A. That is what you are having. I turned the F here has been turned to MA, then I repeat the whole, this is what you have here, right? So by that one, you can actually like eliminate eliminating a few times there, you are going to have this. You can eliminate the hair out, and by the time you eliminate the hair out, you are going to be left with change in Ke, right, is mv squared minus u squared over 2. This is what you are going to be left with. So you can also open the bracket to see, because now you need to start from rest, and then the body has to be in motion. Every object or a body that is in motion, continually going in motion, must have started from rest, right? So if we want to bring that up, you can say change in Ke is equals to half mv squared minus half mu squared. So this is what you are going to have. Right, that's what you are going to have at the bottom. But if the kinetic energy is starting from rest, if a body is starting from rest, right, the u there will be 0. We all know that the u there will be starting, the u there will be equals to 0, right? So if this is equals to 0, you know what you are going to have, because we said that the body will always start from rest, right? So since the body starts from rest, right, i.e., it means that u will be beginning from 0. And if you put that 0 into this place, you are going to be having Ke is not going to be a change again. There will not be a change there again, because nothing is changing, right? So that then you are going to have Ke is equals to half mv squared. Right, this is what you are going to have. This is the proof using kinematics, and then this method is called the algebra method. This is using algebra. If you use the algebra, this is what you are going to have. Right, so similarly, let's do the other one. That is half. When you turn this to 0, all of this cancels, right? Those things cancels out. Those ones you are seeing there, they cancel out. They cancel, and then you are going to be left with this. So the other method I'm going to be using for you now, let me start that one afresh again, is the derivation of kinetic energy using algebra. Now we have done algebra, so now we are using calculus. Yeah, using calculus. Right, so this is the second method I'm going to be showing you. Also, you start again from this is going to be straightforward. You introduce your work theorem, work energy theorem. So from the work energy theorem, you know what you are going to have. i.e., from there you are going to have the change in Ke, just like I've written, is equals to work, right? But here, since this is calculus, we are going to be doing some integration here, and the integration and differentiation we are going to be using here, we are going to be changing the terms. So right, like the displacement you had here, the displacement you had, which we put out here, will now be written. You can write this as r or as s, whichever you want to. So just better to write it as r, right? So which is probably the best to use, so that you won't mix it together, right? So if you continue from there, you are going to have introduce that, right? You know what is the work, force times distance, right? So you are going to say that the change in Ke will be equals to the integral of f, right, multiplied by dr. which is a displacement. But you know that this force now will be also in terms of how, you know, how we write our terms here in integration and differentiation in calculus generally. So this will be in terms of how, right? So once you have this, you still recall that since F is equals to MA, right? So since you want to integrate here with respect to the how, so that F is in terms of how. That's what that how in bracket means. So if you substitute this MA, right, into that F, right, you know it won't be in terms of how again because there's no how into this place. So you remove the how from there, right? But this is how the formula should look like from the beginning, right? This is how the formula should look like, right? So but later on, if you substitute, you are going to have the change in KE to give us the integral of MA, right, multiplied by dr. Yeah, you see that I've just changed this to this. Now it's not, there's no how here again, right, because this is not in terms of how again, right? So the next thing we also have to do is also to recall again that since this A we are seeing there can still be broken down. That A you are seeing there is the acceleration, the M is the mass. The A here can be written as change in velocity over change in time, which is equals to give us the V over dt, right? The V over dt. So if you substitute that, you are going to, right, this is A. So this A you are having here now is what you are going to put in this last expression, right? So if you have that, this is what you are going to be having at the end of the day. You are going to be having change in KE, right, which will give us the integral of M. Now you are going to multiply by dv dt, but don't forget we still have the dr at the back, right? We still have the dr at the back, so you have to put it. There's also dr here, right? So this dr here is the same thing I'm putting here, right? So that is the dr you are now going to be putting here as multiplied by dr, right? But the mass here has to be moved outside. We are trying to write this in differential terms, right? So to get the function, we are going to, what I'm doing here is just to, you are going to write the function in terms of like a differential term so that we can integrate and everything we are having here can be in agreement. So from there, the mass remain constant. You have to put out the mass because the mass here is behaving like a number. You should understand what I mean by that. So you just have to, a constant here, the mass here is a constant term. You have to move it outside so that your change in KE becomes M dv dt multiplied by dr, right? So this is what you are going to have. But we can do a change of term here. It's allowed here to do a change of term. You can do a change of term for these two guys, right? You can swap them. It's still the same thing. A times B, same thing as B times A, right? You can swap both. If you swap those, you are going to have something like this. The change in KE, just to fix into what we are doing, will be M, right, dr all over dt, right, multiplied by dv. That I've just done the same thing. I just moved the dr in because it will be more useful if it comes in and you know what that is equals to. This is just like, you know what this is going to become, right? This is just like how, don't forget how is the displacement, it is the time. Displacement over time is still velocity, right? So if you don't forget, since the r all over the t is still velocity, don't forget. So it implies that the change in KE can also be written as m, right? Then this turns to v, integral of v dot dv, Now it's easy for me to integrate. Can you see that now? So we can actually write that to become something like is equals to m integral of v dv, right? So since we have integral of v dv, now we can integrate. If you this is the last thing I have here, right? That is the last thing I have here. From there, you can now integrate that. If you integrate this expression, right, that expression, if you integrate it, you know how integration goes. You are going to be integrating from 0 to like from the initial, which is you are going to have upper limit here and then the lower limit, right? So you are going to be putting, that is from the v, let's put v here, v and then u, right? So when you are done, you put the upper limit, you put the lower limit, and what you are going to have as a result. Firstly, integrate. If you integrate, that expression, that particular expression, you are going to have change in ke. We are still going to have change because now we are integrating upper limit and lower limit. Yeah, so we are going to substitute. So normally we are supposed to have m. This will give us v squared divided by 2 again. That will give us v squared over 2, right? So probably we are going to have plus c, plus the arbitrary constants. But now that we have defined upper limit and the lower limit, we can just put the u and the v. So by the time you substitute v upper limit minus the lower limit, at the end of the day, you are going to have change in ke to be equals to m, right? So you are going to have v squared over 2 minus u squared over 2. That's what you are going to have. So if you probably move the m inside, you can have the change in ke to give us half mv squared minus half mu squared, right? So that means if you apply this m here and you apply this m here, so the m comes in, and you know what we said, that the body we know that the kinetic energy of a body at rest is 0. So when the body is at rest, so you say when the body starts at rest, abi, so you say u is equals to, you say the u will be 0. So if the u is 0, you can as well substitute that 0 into this place. Then you are going to have your new expression will now be, which will not be changing ke again, right? It will now be ke itself, because now there's no change now, right? We have assumed that the start of that particular body is 0. The kinetic energy, the velocity at the beginning of that motion is 0. At rest is 0. So you are going to be left with ke, giving us half mv squared. So this is the last expression you are also going to have for that. So this one that I have just derived now is the kinetic, using the kinetic energy of any particular object or body in motion using calculus. So thank you for watching the video.